So usually, all this right from this chapter again, I have started, recording it and uploading it in YouTube. So in case if I forget to do the recording, one of you can, remind me. If you don't see it getting recorded, you can let me know. Okay, so far we have seen some important topics and properties of fluids or fluid mechanics, right? Mechanical engineering, the paper or the one of the semesters will be getting fluid mechanics 1, fluid mechanics 2, something like that. Okay, so we are here. Okay, so we did fluid statics. We talked about these things. Then Bernoulli's theorem, fluid dynamics, right? Moving fluid. Then we talked about sticky fluids like viscosity. Then right now we are doing surface tension. So in the last class we talked about some important concepts or important derivations and concepts and surface tension. So the important things to remember here is surface tension is not Newton, it is Newton per meter, right? So force per length. And another way of understanding from a microscopic point of view, how to understand surface tension or what is the root cause of surface tension, right? What is the root cause of friction means you will say there is some roughness between two surfaces, which means between one surface and the other surface, the microscopic gaps will go on fill it up. So that's why you cause that there is a friction, right? If there is no microscopic roughness, right, then one surface will just slide on the other one, right? So there is no friction at all. But that is, so very similar to that. You need to understand what is causing the surface tension. So for that only we talked about, I gave you some extra points here in the. I think maybe I need to add some more points here in the handbook. This diagram is it? It's a lot of chemistry. Okay, I didn't know that. I thought it was there in the physics book. Are you sure? Okay. Can you put your phone? Anybody else remember going through your book? What is there? The diagram does not look the same, but this is the same concept, right? You see, I'm in page number 265. So, people, if you have your textbook, go to page number 265. So it talks about surface energy, right? So the first figure 10.16 A is a molecule which is inside the surface, right, like this, and B is something very close to the same. Unfortunately, this is the kind of diagram where only if you see it like this, it will make more sense, right? If you see it like two different diagrams, it will not make more sense. Molecule inside a liquid, forces on a molecule due to others are shown. Direction of arrows, same for a molecule at a surface. Yeah. Balance of attractive AI and repulsive forces. Okay. Okay. So we talked about microscopic understanding. I hope you are taking down some good notes. Okay. So the potential energy here is higher. Here the potential energy is almost zero because net force is zero. So here we say that the surface alone will be having a energy. Yeah, that is what is the surface energy divided by area. That gives you the surface tension. We are given some examples here. You see Mercury has got a high surface tension. Water is very low. So water is even smaller than that. So we talked about this simple numerical, right? We talked about this work done. I told you when you are talking about surface tension, the surfaces of the liquids should be imagined something like a membrane, right? Elastic membrane, something like a balloon material. So when I pull it out, I have to do some work. And the moment I leave it, it comes back, which means whatever work I did is stored as potential energy, right? So that's the important thing. So work is equal to the energy stored. Then we talked about wetting the glass by water and glass and mercury and glass, right? Mercury does not wet, whereas water wets it. We talked about the acute angle and the obtuse angle, right? So that is what is called angle of contact, and this is constant for a given uh, combination, right? So I told you, I showed you some pictures from Google about the lotus leaf, right? So if you, when you are near some pond where you have some lotus leaves, when you drop some water, right, it will not stick to the leaf at all. Okay, it will be forming something like a spherical balls, something like mercury on the glass. We talked about this lower meniscus and upper meniscus, right? And the reason for this is again the same concept. So that's why I tried to give this in a what do you call, like a tabular format, so that you can easily compare it and study it. Okay. Of course, I'm not saying that this handbook will replace the textbook. Definitely, you have to study the textbook, but this will give it in a different way to understand the concepts. Okay. Particularly if you are attending the classes, definitely, if you go through the handbook, it will make a lot of sense. People who are not gone through the, people who are not there in the class, obviously, this handbook is going to be difficult. Okay. Maybe it will make some sense from your school classes, but my suggestion is you have to attend the school classes over here, handbook, class notes, textbook. All these things will help you. From each source you'll be learning something. Okay, so you have to keep accumulating your knowledge from different sources. Maybe you watch a YouTube video, you will learn some more. Right? Maybe you try to do some experiment, you will learn something else. Right? So try to learn as much as possible from different sources. Okay, we talked about excess pressure, right? I told you when you blow a balloon, right, the pressure inside is higher. So the membrane is kind of, the balloon membrane is kind of, having an elastic force acting this way. Okay, which means to say that when there is a force this way, how come the membrane is not moving? Because there must be an opposite force, equal and opposite force. And when I say force, since we are talking about the gas built inside here, right, in the case of a balloon, I can say pressure. Okay, and the same thing for a bubble, the same thing for a liquid droplet. But then bubble has got two surfaces, so we said it will be, instead of 2T by R, it will be 4T by R. Okay, so I told you two more derivations are there in this. Okay, so we'll do that and then we can get started with the numerical. Another piece of information I would like to share is um, these handbooks. Earlier I had displayed it in Amazon sometime back, like February or March, at the beginning of this year. And because of this COVID and everything, we have removed the listing. But now, we are again, uploaded it. So if any of your friends or any of your cousins or anybody who's wanting this book, they can order it directly from Amazon. You can come to our website also, but you know, if you want to get it from Amazon, you can do that also. Just a piece of information, because I see sometimes students asking, sir, is it possible for others to get the book? And yes, you know, the book is available for everyone. So last year we started, but then because of the COVID situation, we were not able to continue. So we stopped it for a while. So I can show you. I have to go for it. Just go for Amazon, and then if you search for class 11 or yeah, so it's available over here. So people who want it, they can order directly from here. Same thing is available for class 12 also. Class 12 physics handbook. It's also available. Okay. Or if you are finding it difficult to find, you can search for author's name, Guru Prasad Narayan. You can search it that also. Okay. I would say, in my opinion, 12th physics handbook is much more better. 11th physics handbook, you know, of course, it is very good for the CBSE preparation. I'm sure some of you or most of you are using it. And I hope you are finding it useful, right? But when it comes to entrance exam preparation, I need to add some more materials. But for now, whatever is available, you know, I'm just displaying it in the Amazon. So if you are finding it difficult to search it here, you can search it through the author's name. Yeah. So when you type for the author's name, you will be finding it. Okay. Or another method is, you know, if you don't want to go to Amazon, Flipkart, I'm still trying to, you know, upload it, but it is asking for some ISBN number, so I was not able to, you know, upload that. But if you go to our Guru Academy Labs website, you should be able to. Okay. Yeah. So either you can buy it in Amazon or you can buy it in this thing. I mean, people who are studying here, you don't have to buy it. But I'm just talking about others who want to buy this books. Okay, it's just a piece of information I wanted to share in case anybody is willing to buy it. Okay, so coming back to this topic here, let's see. So derivation is a bit simple, you know, it's not very difficult, but understanding the starting point is a bit tricky. So pay attention. So suppose if you have a droplet, imagine that you have something like a balloon, right? Imagine in a soap bubble, you will have a bubble like this, and as I start blowing, right, what happens? It keeps increasing. So that means imagine initially it is of this size, and now it is, you know, increasing in size. Something, you know, let's say I'm blowing it. That means the size is increasing. So what happened here was, initially the radius of the sphere was r. Okay. Always remember, we are drawing a 3D object in a 2D. Okay, so if you are seeing a circle, you should imagine that it is a sphere, it's not a circle. Okay, so unfortunately, we are living in a 3D world, but then when it comes to learning, we don't have a 3D board, so we have to depend upon the 2D board, 2D notebook. So this excess radius, right? How much excess radius that happens? So that is your delta R. Okay. So look at this work done by excess pressure. So what was I was blowing some air through the pipe. Let's say this is a pipe and blowing some air, which means I had to do some work, right? I have to give some energy. So that means work done by the excess pressure. So the excess pressure. So this is from this situation. Let's say it is going to a extra pressure. So that is a P excess. So you know that pressure into volume is something called pressure energy. We talked about, right? So pressure into volume is Newton per meter square into meter cube. So this and this cancels. So I'll be getting Newton meter, which is work done. That means you should know that by this time you should know that pressure into volume will give me the work done by excess pressure. So excess pressure P excess dot delta V, that is the increase in surface energy. So P excess dot delta V. And what is surface energy? We already studied in the last class. Surface tension. Surface tension T is equal to surface energy divided by anybody? Area. So that means T into area. So that's what increase in surface energy. So surface energy is equal to this into this. I'm just doing the cross multiplication. So what is the change in volume? This is simple mathematics. So you have a sphere and then it is increasing to a bigger volume. So what we do is, since the increase is very, very small, right? The important formula for, say that
we
again.
need to we need to find the volume such that the radius is r plus delta v. That is the new volume, and
Okay,
then first volume is when radius is r. So we need
okay,
to subtract the new volume minus the older volume.
okay, very good. So what Chaitanya is saying is, okay, I really appreciate Chaitanya because he's sharing whatever is going on in his head. He's able to share it. Okay, that kind of um, open-mindedness you all of you should get. Actually, folks are keeping quiet and you are not interacting at all. It's very poor actually. When you go to college, when you go to profession, you're going to struggle a lot because sometimes what you have is one thing, but what is that you're going to share with others that is more important. Okay, if you don't share it, if you go to interview, nobody knows what you know. So you have to open your mouth and share it. So what he's saying is change in volume is nothing but volume final minus volume initial. Okay, which means to say 4 by 3 pi r cube, but the new r is r plus delta r, the whole cube, minus 4 by 3 pi r cube, because the r is the original radius. Okay, so this is what he tried to say. Okay, but then here I've used a different formula. So since the increase here is very, very small, right? So if I assume that this increase is very, very small, what I can do is another way of understanding volume is cross-sectional area into distance. Remember this pi r squared into h. What is the volume of cube? A squared into a, which means a cube, right? What is the area of cuboid? L into b into h, right? So take the area and then multiply by the height. So if you take a cylinder, pi r squared into h. So this is your area and this is multiplied by the h. That will give me the volume. So here, if you do it by this method also, you'll get the same answer. Okay, but then again you have
Pi
to do
r
some
square into r.
approximation. Yeah. So what is the area of the sphere? So delta V is equal to 4 pi r squared is the area of the sphere, right? Surface area. into what is the distance? It increased by a distance of delta r. So that means this area into this will give me only this increased area. So take it down properly. Okay, this is a confusing part, so everyone take it down properly. So 4 pi r squared into delta r. Okay, so that is your delta V. So that's why you are getting delta V like this. Here change in area. What is change in area? 4 pi r plus delta r. Why r plus delta r? This is the new sphere. This is the old sphere. Okay, initial is the yellow one, the pink one or the white one is the new one final. So that means r plus delta r is the new radius. So 4 pi r plus delta r the whole square minus 4 pi r square. So do the cancellations. After this it's your job. Okay, I don't have much to explain for. Again, as we always do, what we do, whenever it is delta, the delta r means it's a very small number. Okay, something like 0.02, something like that. So when you do the square, right, square or the cube terms will go away, which means this r squared delta r, the whole square term will get cancelled out. I think we are cancelling this also. R squared cancels. Sorry, this one we are leaving it. R squared r squared and r squared will cancel, minus r squared is here. There is a delta r here, there is a delta r here. So these two things you have to do the math. Maybe we can write the last step and we can try this. So far, any doubts? Anybody? Pxs dot 4 pi r squared into delta r is equal to tension, surface tension into 4 pi r plus delta r the whole square minus 4 pi r square. Because we are talking about the change in area, right? Delta A, this area is. So now this 4 pi, I can take it out commonly. So that 4 pi and this 4 pi will cancel. Pxs is what I am interested in. So delta r, we can try to get it cancelled out. So I'll be getting T r square plus delta r the whole square plus 2 times r delta r minus r squared. So this r squared and this r squared will cancel. This delta r the whole square is a very small time, right? I told you 0.1 the whole square will be 0.01, which means it's even smaller. So I think I can ignore this also. It means I will ignore this. I will cancel this. So what is left is Pxs delta r. So this delta r, this, if you want, I can write it one more time. So T times 2r delta r. So I can cancel this delta r and this delta r. So what is left is you will get the final answer. So this is what I told you in the last class. Just take it as a formula for now, and we will do the derivation in the next class. So T into 2r. Okay, am I making any mistakes here? Okay, there is a r squared here, so I will forgot this also. So this r and this r will cancel. So r will come in the bottom. So Pxs is equal to surface tension divided by, sorry, 2T divided by r. So this formula you have to remember for many of the numericals, particularly for your NEET and JEE type of problems, okay, or any other entrance exams. Any questions? Anybody not following anything? Some of you told me that you are having some school exams going on, and you are not able to attend the classes. So that's why I'm uploading the YouTube videos. The YouTube I'm uploading all these classes. Okay. So it's your responsibility to go through it. Okay. And then if you need some help, you can always ask me after the class. Okay. But you have to go through the YouTube before you can. If you have any doubts, I can do, or I can ask Satya Madam also to help you. Okay, you have to check with them.
Why do we cancel the delta R square? Is it very small?
Yeah, delta R we are talking about compared to R. Let's say R is say 1 centimeter, and then this delta R is going to be something like 0.1 centimeter, which means when you say delta R the whole square, it's going to be
It will
even
be
more
very small.
smaller. Yeah, so 0.01. So that's the reason why it's okay to ignore this. Okay. Suppose if they said that the delta is very big, then this final formula will not work. Okay, which means you have to go back to this basic formula. That's why I always say formulas will not help you in real life. So you have to understand the basic underlying principle. In a real life situation, let's say if your delta R is not so small and it is comparatively, let's say this is 1 centimeter, R is 1 centimeter, and let's say the delta R is say 0.3 centimeter, then you see it's almost 30%. In that case, you cannot completely ignore the delta R. Maybe delta R square you can still ignore because it's 0.09. So depending upon the situation, you have to decide whether it is okay to ignore or not. I think some time back I told you about the LED TV and ice cream example, right? Ice cream or chocolate example. So when you are buying a chocolate for 10 rupees, if you say I have only 5 rupees, the shop owner is not going to give you. Okay. Because 5 on 10 is 50% money. But if you are going to buy a LED TV which is 40,000 rupees and you say that to the shop owner, I have only 39,995. Is it okay if I leave that 5 rupees? He will happily take it. Why? Because 5 on 40,000 is very, very small amount. Okay. So that means in real life, it's not the absolute value that matters, it's the relative value that matters. And that's what we studied as relative error. If I'm measuring a table and if I'm giving a 1 centimeter error, it's not a big deal, right? But maybe 0.1 centimeter would be better. But if I'm measuring the distance between Coimbatore and Chennai, and if I have some 20 meters error, does it matter? Not a big deal, right? So it depends upon the situation. Okay, any questions? So I hope you are taking it down properly. Okay. So very simple derivation. Again, conceptually speaking, this excess pressure is slightly confusing topic. Okay. So the basic idea here is the concave side will have an excess pressure. So if you see this diagram, if you take a upper meniscus like this and a lower meniscus like this, the upper meniscus will be looking like this, which means this is the concave side, whereas here this is the concave side. Okay, so pay attention. Which means this side we say if this is atmospheric pressure, this side the excess pressure will be. What do you mean by excess? The extra pressure. Okay, which means this pressure will also be there plus the excess pressure. But if you take the lower meniscus like this, if this is P atmosphere, we said the concave side, the pressure will be higher, which means this side it has to be lower, which means the excess pressure should not be added, it should be subtracted. Okay, so this is an important conceptual question. So take it down. So again, let me repeat it one more time. The concave side will be having the higher pressure, whereas this side here is the concave side, which means here the pressure is higher, which means here the pressure should be lower. Here the pressure should be higher. Okay. Again, if you are not able to imagine why it should be higher, again, you have to go back to the balloon example. Okay. So when you blow a balloon like this, compared to the atmospheric pressure, here the pressure will be higher. Okay, so that means you can imagine this is a balloon. This is the concave side. So the concave side, the pressure will be higher. Okay, because the forces are acting like this. Okay, everyone following that? Anybody not able to follow that? So to balance this forces, right, that must be a higher pressure. Only then that will be a balance, okay, equal and opposite force. Okay, so that is, and again, as we talked about earlier, when it comes to bubble, right, like a two surface, then it will be 4T by R. Why? Because it will be 2T into 2, because two surfaces. So that means it will become 4T by R. So this is a very interesting experiment. Okay, we have this experiment in the lab. Okay. So if you take you can observe this in a straw also, but then when you insert a straw inside your juice or a water or something, right? Let's say this is straw. This is a water. What will happen is you will think that the water level will be here. Okay. In reality, if you carefully observe, right, very, very closely, if you observe this, you will see that there is a slight rise in water. This rise is very, very small because the straw is pretty big. You are breaking, Chaitanya, your voice is breaking. Say that again. Your voice is
Can you repeat
breaking
what you
something.
said? I wasn't able to hear.
You did not understand this? Everyone able to hear me or not?
Sir,
Any
can you
issues?
repeat what you said, sir?
Okay. For everyone,
Sir,
can I understood
but
what you are asking.
sir, before what you were saying, I wasn't able to understand, sir, because the voice was breaking.
Okay. What about others? Is my voice breaking or are you able to listen properly?
Kind of breaking, sir, in between sometimes.
Okay. What about others?
So for me, it's clear.
So even for me, it's clear.
Clear.
So it's clear
For
from
me
this.
also it's clear.
Okay. So which means to say that, if again, as I told you some time back, earlier I was using this Geo dongle and now I have changed to ACT fiber net in the office. So earlier, many students were complaining that there was some, voice breaking and stuff like that. That's why I changed to this. So I don't think there will be any issues with the internet over here. Okay. So from what you are saying, looks like some of you are having some, breaking voice means maybe you have to check your internet. Okay. So my internet seems to be okay. If all of you said that, you are not able to hear me, then probably it is internet on this side is a problem. Okay. Okay. So for now, I would say my internet is okay. So please check your internet. And if you are already attending a lot of classes in school, right, probably your data will be low. So maybe that will also cause some error, okay, some voice breaking issues. Because you will already be using it for more than say 6 or 7 hours. And then the last 1 hour, if you're sitting here, obviously you will not be getting enough data. Okay, so coming back to this, what I was trying to say here is, suppose if you introduce a very, very, very small tube like this. Okay, so this kind of tubes, which is having extremely small diameter, right, is called capillary. And I'm sure this is the word which you're using in your biology also, right? Is that right? For very small tubes in the plants, you use capillary, right? It's called capillary action. So what happens here is the liquid from here, when the diameter is very, very small, the liquid from here will try to rise up. So it will rise up to certain height. And this height, right? This liquid rising in a very small tubes called capillaries, called capillary action. Chaitanya, following?
Yes, sir. Yeah, able to understand.
So even with your straw, you will be able to see it. Okay, provided the straw is it's not the paper straw. It should be like a plastic straw where you can actually see the liquid, right? So in that case, you will be able to see it. But then since the straw is pretty big diameter, right? So comparatively speaking, the diameter is very big here. So which means to say that this rise in water level will be very, very less. Okay. But if you take extremely small, thin tube, right? Maybe you can take this in your, what do you call it? Refill pens, right? So not refill pens, the lead pens. If you take the inside tube, right? You take a old pen where you have this in one side, the same. What do you call it? Is it called the refill or we call
Refill.
this? Yeah. So if you take that, it will be having a very, very small diameter. So if you put this inside the water, right, you will see that the water is rising to a certain height. Okay, so try this experiment. Again, as I always say, if you are trying some experiment, please feel free to send the WhatsApp video. Okay, I can share it with others also so that others can also learn from your experiment. And if you are having some bigger goals, like sir, I like physics very much. I want to learn more. I want to get into great colleges. Then I would recommend you to try some experiments. Okay, it's not going to take more than say 15 minutes or 20 minutes. Okay. No, sir, I'm just just like that. I'm studying, get some marks, and keep clearing, and then move on to something else. Means then probably you don't have to do anything. Okay, but if you have some higher goals of becoming a scientist or a good engineer or something like that, then you should try some practical experiments. Sitting in front of computer is not going to help you, in science. Okay, so coming back to this topic, this is what is called capillary action. Why does this happen? Again, the idea is surface tension and this cohesiveness, right? Cohesive forces, right? Sorry, adhesive forces. So you see this glass material and this water is having some attraction. So because of that, this is able to get, so this glass molecules are attracting this. So which means the water level will slowly rise. Particularly if it is very, very small, it can rise very easily. And if you are wondering, sir, how come if the diameter is bigger, it's not rising much, but if the diameter is smaller, it is rising to certain height, right? This we have this experiment in the lab. Okay, maybe I will show it to you. Okay, people who are here, I will show it to you. And if possible, I try to take next class. We remember, okay, so we are coming early. So maybe I'll try to take a video and send it to you. So the way I understand this is, suppose if you take a bigger tube like this, let's exaggerate this. So you have so listen carefully. If I say the water level is rising to a certain level like this, so you see the molecule over here will also attract this molecules over here. But then somebody also, the glass, this molecule is also attracting this, which means this will try to rise this way, right? That's why the angle of contact will be acute here, right? That's what we studied for water and glass. So that means if you're wondering, sir, will this molecule attract this? Yes, this molecule will also attract this. But this molecule is also getting attracted to the glass. So it means whoever wins, that is going to be bigger, right? But suppose if I make this tube very, very thin, something like this, then what I'm trying to say here is this will rise to a higher height. Why? Because the concept I can think of here is, the imagination I have here is, the molecule here, is it attracting this? Yes. But then this, you do not have this many molecules. You have only less amount of molecules, which means the effect of the glass is going to be more, which means it will be able to keep rising this up. And that's what we talked about this in the earlier class. What was the name in the biological terms in your plant? Xylem, right? Xylem. So xylem, anybody know the diameter of this? I don't know. I don't know. Okay. If any of you can tell me the diameter, not right now, maybe you can find it out and let me know. So obviously, I'm sure it should be very, very thin. Okay, maybe you can ask the. Cross cell supporting species mean the cell diameter range from 14.8 cell diameter stem diameter scale. Again, I don't know much of biology, okay, but looking at the numbers, it looks like it's something in the order of 3.1 mm would be very big, 0.1 meter diameter. This is 15.8 micrometers, right? So that's 10 power minus 6 or 10 power minus 3 millimeters. So obviously you can see that these are all very, very small numbers. I'm not sure why these numbers are very big. Again, biology people, you do the research and find it out. Okay. But from physics, what I can tell you is if the diameter is very, very small, the rise will also be higher. Okay. That's what I'm trying to explain. There are two types of derivation to arrive at the same final result. Okay. This is using the excess pressure. This is using the simple concepts which you already know. Okay. But in your textbook, in the NCERT textbook, they are given you this proof by excess pressure method. Okay, so definitely in your school exams, I would say this might be expected, but nothing wrong if you do this derivation also. So let's talk about both the derivations. And here in this diagram, you can see that as the diameter of the capillary gets smaller and smaller, what happens? The height keeps increasing. That's what we are trying to show here. One more thing I forgot to show was mercury. In the case of mercury, very interestingly, the mercury level will drop, okay, because it will be going downwards, because it try to go away from the glass, okay, because it doesn't like glass. So maybe I can explain that one more time. So suppose if I take mercury here, right? Let's say this is mercury. It's a mercury level. If I put a capillary tube here, the level is not going to rise this way. Instead, the level is going to drop like this. This is a very, very interesting situation, right? And the reason is very simple, because water and glass like each other. Water and mercury do not like each other because the cohesive forces are less, which means this is what we'll take as height. The capillary height will be capillary rise. Of course, here we call it as capillary rise. Here you would call it as capillary rise, which is negative, or you can say capillary drop. So this is for mercury. Okay, this derivation, let's quickly do this. Very, very simple, nothing difficult at all. Just 2 steps, you'll get the answer. So suppose if you observe or know what is happening on the top surface of this, right? Top end of this. So just to make it easy, I'm just drawing it a little bit bigger. So the top surface is going to look something like this, which means it's going to have a cup shape like this. Okay, why? Because the liquid is like this. If you're seeing it from the side, you're going to see it from like this. But if you see it from the top, you will see a circle, right? So you know that there is something called surface tension. So the tension is going to be acting this way. Okay. You know that this is your angle of contact. Yeah. So surface tension T. So what I can say is I can split this into 2 components. One will be, if this is theta, this is also theta. If this is theta, this will be T sine theta. This will be on this side, it will be T cos theta. Same thing will happen on this side. So T cos theta will be on the top. T sine theta will be acting the sideways. So you can imagine that, just for simplicity, I'm showing only the 2 ends. Okay, that will happen in all the ends. Okay, you see the T sine theta will be acting everywhere, which is where it is touching the glass. Similarly on the other side also. Okay, again, it's a 3-dimensional picture. Very hard to show it properly. Okay, this is the best I can show. So you have to imagine, just because I'm drawing here doesn't mean that it's only here. It's on every side. Similarly, I'm showing only the T sine theta on the sides. What about the T cos theta? The T cos theta should be acting on all the sides. So that will be a T cos theta here, there will be a T cos theta here, there will be a T cos theta here. Everywhere there will be a T cos theta. Anybody not following this? At every location there will be a T cos theta and T sine theta. What can you say about the T sine theta? Somebody is pulling this way, somebody is pulling this way. So both will. Somebody is pulling this way, somebody is pulling this way. Both will oppose each other, which means they will cancel each other.
Cancel.
Okay. Yeah. Whereas the T cos theta, everything is acting upwards, which means I need to add everything. Okay. So what I'm going to do here is, since the length, I know the length of this. If I know the diameter of the radius of this burette of this glass tube, right? Yeah, I think I've taken this A, which means the circumference of this circle will be 2 pi A. So what I have done here is, listen carefully. T cos theta is the force, so I'm multiplying it with the length. Okay. Why would I do that? Because how is surface tension defined? Surface energy by area, that is correct. Any other formula? What is the definition of surface tension? The very first definition. Force by
Length.
length. Very good. That means if I want force, what should I do? I should multiply by the length. So that means this surface tension is acting in the length of 2 pi A. That is the circumference. Okay. So it means the surface tension is force. Remember, T is not tension, it is surface tension, which means it is not Newton, it is Newton per meter. Okay, so for 1 meter, it is T cos theta. So how much it is for 2 pi A? So that's why you are multiplying by the length. Okay, now come back to the basics here. So listen carefully, very simple. So you know that the water level is, staying somewhere, standing up like this. So this is a water level here. So this is the extra water level. So what is the basic formula we studied? What is the basic property of water? you put a line over here, the pressure here and the pressure here has to be the same, right? That's a very important property in liquid, which means this is P atmosphere, right? Because nobody else is acting, it's only the P atmosphere which is acting here. So take down the drawing properly. I may not have given all the details. Whereas here, right, this is P atmosphere. Whereas here, who is acting on top of this? It's the P atmosphere plus this liquid weight. Okay, so this liquid weight is also acting on this part. Okay, so that means what I can say is maybe I have not given the steps here properly. So if I take this X and Y location, pressure at X should be equal to pressure at Y. Pressure at X is P atmosphere. Pressure at Y is on top of this, there is still pressure, atmospheric pressure is acting, right? So that plus this liquid column. Oh, okay, wait a minute, don't take down this. What I have done here is I have not considered the pressure, I consider the forces. So this is a force acting upwards, right? Somebody is pulling it upwards, and the weight of the liquid column is acting downwards. So that means I'm not considering the pressure. Maybe you can do it by the pressure term in the next derivation. Okay, this is coming for the next part. So I don't want to confuse you right now. So we'll come to that later. Pressure method is coming in the next exercise. So right now, somebody is pulling it upwards and somebody is pulling it downwards. Who is pulling it upwards? T cos theta into 2 pi a. Why? Because this is Newton per meter multiplied by the meter length. That should be equal to who is pulling it downwards? Weight of the liquid column. What is weight of liquid column? Mass into gravity. Okay. What is mass of the liquid? Density into volume. Okay, capital V. Don't forget small v is velocity. What is the volume of this capillary rise? Pi r squared into h. Right. So h is the height of the capillary rise. So that means the height is going to be somewhere here. So h. So that means density remains same. Pi r squared is I'm taking it as a, so pi a squared into h into g. That's all. So this is the underlying principle. If you don't know this underlying principle, you cannot do the derivation, you cannot understand the numericals. Okay. You can simply apply the formula and get some answers, but you don't know what it is. Okay, so that's why given here the principle is very important. Force acting upwards should be equal to the force acting downwards. So surface tension pulling the liquid upwards for the entire circumference. So force acting upwards is equal to the, maybe I should have written the weight of the liquid column here. Okay, so take it down. Maybe I missed it. Okay, so I need to update it in that. Weight of liquid column in capillary rise. Okay, so after that, it's very simple. Just do the cancellations and do the math, and you'll get that. Okay, so this anybody can do it. So this is the part which you need to pay attention. So a and a cancels, pi and pi cancels. So if you do the math, you will be getting this. Okay, so P is equal to rho g h a divided by 2 cos theta. Any questions? Anybody? Any doubts? Everybody understanding capillary rise? Again,
Yes,
these are
sir.
all things. These are all things which you cannot understand unless you actually see the experiments. Okay, so maybe I'll try to find some YouTube videos, or I'll try to upload some videos. Okay, so this is a easier method. I told you it's it's a force method. Okay, this is called the force method. Another method is the pressure method. Okay, or the excess pressure method. So let's go to the excess pressure method. Excess pressure method is also very easy. Okay, nothing very difficult. So understand the diagram. Understanding this diagram is important first. So we are talking about capillary rise. We are talking about something like a lower meniscus in this particular example. So if you consider the radius of this bubble or this, right, this is the center of the curvature. Okay, so the center of curvature is imaginary point somewhere here, where this will be taken as your radius. So this is the radius of curvature. Earlier we had taken this diameter of the tube as A. Now you should know why I have not taken R, instead I took it as A. Okay. So radius of the tube is different radius of the this concave surface is another thing. So take it down properly. So this is a concave surface. So if you are wondering, sir, using R would have been better. Well, we are using R for some other purpose. So that's why we use GA here. Okay. That means this distance, this is A, this is also A, radius of the. So take it down properly. This is radius of tube. This is R is radius of the concave surface. However, the interesting thing is, I told you this is an imaginary point, right? If I ask you, okay, measure this radius of this concave surface, means it's going to be very, very difficult. Okay, measuring the radius of the tube is very simple. You take a vernier and you can measure the diameter to find the radius. But measuring this is not going to be easy, which means we will be using some trigonometric concepts. So you know that this is your angle of contact from the table, right? You can find the theta. Okay. Ashwin, can you give me your textbook? Let's see. That is the angle of contact. I'm in page number 267. And drop and bubbles, capillary rise. I'm looking for a table which gives you surface tension and the angle of contact. Is there a table like this? Surface tension is there. Table 10.3. 6. Angle of contact is not given. Okay, I thought there is a table which shows the angle of contact. Okay, for a given combination, you can always find the angle of contact. Okay, you can do a Google search and you'll be able to find it. So what I'm trying to say here is, I can say that I can find R in terms of A and theta. Okay, that's the point I'm trying to make here. You see this diagram. So if this is theta, then this is also. So if I draw a line over here, if this is theta, listen carefully, this is 90 minus theta. If this is 90 minus theta, you see the radius and the tangent will also always be 90 degree, which means if this is 90 minus theta, this will also be theta. So take it down properly. If this is theta, then this is also theta, alternate angles, so opposite angles. So if this is theta, this is R, you know that R cos theta will be equal to A. So R cos theta will be equal to A because it's the adjacent side. Okay. After that, it's very, very simple. So what is excess pressure? This side is your concave side. This side is your convex side, which means this side it will be P atmosphere. This side will be P atmosphere minus P excess. Okay. So now I think I can use the earlier formula, earlier method I was talking about, the pressure method. So this is again, a bit confusing in the textbook. So take down proper notes. Very simple, but a bit confusing. So the derivation may not have been given properly. So if this point is X and this point is Y, pressure at X is equal to pressure at Y, property of liquid. Okay. Who is pressing on top of X? P atmosphere. Who is pressing on top of Y? P atmosphere plus liquid pressure. But then we bring in another concept here, which is here the excess pressure will be less. Okay. So that means what we do here is P atmosphere minus P excess. That will be the pressure here plus the rho GH. Okay, because who is pressing on top of this means this pressure plus this and then this one. But here I cannot do plus because it is this pressure should be subtracted. So this pressure is subtracted and then rho GH. So for this height, you get taken as rho GH. Okay, everyone following this? So from here, it's coming this in this location to be minus pxs. So after this is very, very simple. This and this cancels, so this comes on this side. So pxs is equal to rho gh. So pxs is nothing but 2t by r. Remember, this r is the radius of curvature, right? Not the radius of the tube. So there are two different radiuses, so don't confuse. What is r? Just now we found that r is nothing but a by cos theta. So r is equal to a by cos theta. So as I told you, measuring r is difficult, whereas measuring a is easy, theta is easy from the table. That means 2t by a by cos theta. So if I want t, this entire thing goes on this side. So t is equal to a cos theta goes here. So I'll be getting rho g h a divided by 2 comes on the bottom. So 2 cos theta. Okay, so take it down properly. That's all. So that's the important derivation. As I told you in your school exams in term 2, I think you will be having some theory questions, which means to say that you have to study both numerical and theory. Okay. And you may get these kind of derivations. So for school exam, I would recommend you to use this expression. This is what is given here. And sorry, textbook. Okay, so let's see what is the last topic here. Soap and detergents. It's a very easy topic. I'm sure you are studied this in your 10th standard or some chemistry or something, right? So anybody remember what is hydrophilic, hydrophobic? Anybody remember that in my chemistry? Somewhere in the 10th standard, I think you studied something. Hydrophilic means liking, right? So liking the hydro, meaning liquid or water. Phobic means hating, right? It doesn't like it. Okay, phobia means you hate something. You don't like it, pure, yeah. Philic means nucleophile, right? So philic means it likes it. So the detergent, what happens is, simply what I tried to explain here is, you must have studied this in your chemistry much better than this. Okay, so just a simple diagram. So one end will be hydrophilic, meaning it likes water molecules. And the other end will be called as hydrophobic. So it doesn't like water. Remember, it's called etymology, right? So if you understand the root words, you'll be able to make meanings for different new words. Okay. Hydro refers to water, right? From hydrogen, water is coming. So hydro refers to water. Philic means liking, phobic means fear. So understand this basic root words, or it's called etymology. If you understand that, you will be able to figure out the meaning very easy. So what happens is, suppose if I have some dirt somewhere, right? So washing it with water alone will not be sufficient, right? Take for example, let's say I'm having a meal in my plate. So in a stainless steel plate, let's say I have some oily food, right? So just washing this with water alone is not sufficient. So what do? We put some detergent. So that means the oil or the dirt will be having some kind of a layer here. Okay. Again, all these things are microscopic levels, so we are just exaggerating, right? So that it's easy for us to understand.
Oil is hydrophobic, right, sir?
Oil is hydrophobic. Yeah, it's something like opposite of water, right?
Because it
So
does not
here,
mix with water.
yeah, it's kind of invisible, so it's very difficult for you to wash the oil away. So that's why we use a detergent. So what we do is, or what's happening in a microscopic level is, if you take a situation like this where this is a dirt, so when you apply a detergent, so you have this detergent molecules. So one end will be liking, it will be sticking to the water molecule. The other end will be sticking to the oil. So this is your oil and dirt. So it doesn't like to go to the water molecule, right? That means they will be sticking to this. Whereas here you have water. When you're washing, you have some water molecules. So that means what happens is, when you're applying all this dirt, this detergent, right? So these hydrophilic sites are going to be on the water side. Hydrophobic side is going to be sticking to the dirt. Once I put a lot of water, right, this entire thing will be washed away. So since these are sticking to this, it will be removing the oil. And this is the mechanism of cleaning the dirt. So take it down. So basically, this is what you must have studied in your chemistry, right? Somewhere in your chemistry. Here, one more point here is, when you apply some soap or detergent, basically the surface tension decreases, right? So surface tension actually reduces. Okay, so thought of getting started with some numericals, but it's already time. So I told you you should get started with the examples. Okay, this time I may have to give you some theory questions also because you have theory questions also for your test, your term two. So prepare for the theory derivations also. Okay, and for the maybe for the numerical, either I will give it as a test where you can write it and then send the pictures to Sunil sir and he'll be correcting it. Or maybe we can have numerical test in the online test method, then theory test will be on the PDF method. Okay, let me quickly go through the textbook pages. Okay, we talked about Pascal's law, right? Pressure acting on the different sides. So go through the textbook. Pascal's law proving we use this triangle thing, right? We did this variation of pressure with depth is your rho GH derivation, right? We did this. We talked about the pressure difference between 1 and 2, right? So here the pressure is going to be higher compared to the pressure over here because of the rho GH, right? Pressure due to the liquid column. We talked about this, right? Same height. Pressure on a swimmer 10 meters below the surface of a lake, which means you should be using rho GH, right? Density of water, you know, G is gravity, H is given. Atmospheric pressure and gauge pressure, we talked about it. That's surprising. I thought it was not there in the textbook, but it is there. So maybe we talked about the Torricelli's barometer, or barometer, whatever you want to pronounce. We talked about the YouTube manometer. We talked about the differential manometer, which I do not know if it's given or not. We talked about the hydraulic machines, right? The pressure will be same. Talked about the automobile shops where they use this. Yeah, you see the car is lifted like this. I even showed you some syringes, right? Syringe experiment. So go back and start doing this this problems. Okay, very simple. You see, even here in the example, they given two syringes of different cross section without needles. Right?
Sir, uh, from Monday we'll start following numericals, sir.
Yeah, before that, you should start solving the numerical. Okay, so start doing the numericals from the textbook, the examples and basic exercise. The more you solve it and then come to the class, you will be learning more. Okay. Bernoulli's principle, we talked about it, right? Bernoulli's equation. Speed of a flux, we talked about it. I told you the etymology here is what is flux? Flux means flow. E means exit. So exit flow. So speed with which it is coming out. That is what it's called. Exit flow or exit speed. We talked about this Venturi meter, right? Pressure differences. We talked about this derivations. Okay. We talked about the spray gun. Everything is covered in the handbook. Okay, so study the class notes and the handbook. Then come to the this thing and start doing the problems. blood velocity, you see, you have some biology related problems also. Okay, I'm sure it will be useful for your biology. Dynamic lift, we talked about this, right? Magnus effect. This is what I told you, there is an error in the textbook. Okay, so I think the arrow should be this way, right? Only then here the air going this way and the air going this way will add up. Here it should cancel, right? So this arrow is shown as clockwise. Actually, it should be anti-clockwise. So correct it. Talk about the airfoil. Viscosity, we did it. Okay. Go through it. If you find any theory which is not clear, you can always ask me. Okay, we can discuss it. This is a very important problem. Try this. Okay. Very often they will ask you this in the exam. Okay. You have a block like this. So what will happen when you answer way to fill? There is a fill mode here. Okay. So your homework is to complete the example problems. Okay. Surface tension also we completed it. Okay. Okay. Here I thought they may have given you the angle of contact, but for angle of contact you should have a combination of two surfaces, right? So for different surfaces, we talked about this. Don't get confused with this SCA, LA. So LA is liquid and what are they saying here? Yeah, yes, yeah, I think L is liquid. So liquid and yeah, here it is solid and yeah. So this glass surface is solid and yeah. PDF is kind of very slow. We talked about drops and bubbles. We talked about the radius. So here excess radius, excess pressure. We talked about the capillary rise. We talked about the soap molecules, right? Hydrophobic, hydrophilic. So I think you have 11 examples. So try this 11 examples and then go to the exercise. Basic exercise, most of them are going to be easy. Okay, so try that. Direct formula substitution. If you have attended the theory classes properly, I'm sure you will be able to attend. So you have approximately some 15, sorry, 15, 19. Yeah, so we have approximately 20. So 11 problems from example and 20 problems from basic exercise. Okay, so try this and come. I may not have time to do all the 20 problems. Maybe maximum I can do some 4 or 5 problems and then get started with the additional exercise. Okay. So it's your duty to work out the problems. Okay. Okay, then thank you all. If you have any doubts, you can stay back. Otherwise, you can leave, but start doing the numericals. Okay. If you're finding it difficult, you can always come here and sit and do it. Okay, Saturdays, that's why I asked you to come here and do the numericals here on the Saturdays. But I think some of you are coming, one or two students, others, you folks are not coming. Okay, so it's left to you. As I always say, as you sow, so shall you reap. Okay, so whatever hard work you are putting in right now, it's going to be helpful for you somewhere, maybe in your entrance exam, maybe in your 12th standard, maybe in your college. Okay. So it's up to you. So thank you all. Bye.
Thank you, sir.